In this video, we will provide an introduction to the ATHENA technical work package, explaining how we are developing a platform to help combat FIMI online. We are going to begin by describing some of the tasks in this work package and explaining our approach to solving some of the challenges that we face. We will then provide a brief demonstration of the system, showing some of our search and analytical tools in action. There are four main tasks in this work package. The first is to source and collect FIMI data. In ATHENA, we have a goal to gather data from at least 500 websites and sources that can be linked to FIMI campaigns. Once we have gathered the data, we will process and store it in our internal knowledge graph, applying state-of-the-art knowledge engineering techniques to uplift the data to rich, highly queryable and reusable formats. We will also develop a FIMI toolbox, a collection of tools and services that can be applied to the data in the knowledge graph to provide further insights such as reliability scores for articles or probabilities that an image or video is a deepfake. Finally, we will develop a dashboard that will support journalists, fact-checkers, policymakers, and more in their exploration of the knowledge graph. The dashboard will provide powerful tools for filtering data and monitoring ongoing campaigns as they emerge. Let's begin by introducing the system architecture and seeing how it relates to the tasks we have established. This architecture provides a roadmap for our discussion of the ATHENA system and all of its major components. Beginning on the left, we have the data ingestion engine, which is responsible for harvesting data from the websites that we target. This engine is designed to be highly modular and extremely simple to extend. Because FIMI websites can be highly ephemeral, a modular, extensible system makes it easy to spin out new scraping tools to target new sources of data as they are identified. We are often asked how we select sources to include in our scraping platform. We rely on a variety of sources to help us in our decision-making process. Websites are selected for scraping based on investigations performed by the ATHENA team into 32 FIMI campaigns, reports written by organizations such as Viginum and the EEAS, and published research that focuses on disinformation campaigns. Data gathered by the scraping tools is passed into the data storage and treatment module, where it is normalized and stored for future processing in a database referred to as the harmonized data model. Data scraped from the internet will be noisy and arrives in a variety of formats. The harmonized data model is responsible for normalizing this data into a consistent representation. We borrow some concepts from STIX 2.1 and distinguish between two types of entity in our model: observables, which are blog posts, Telegram messages, etc., and identities, which are the channels or organizations which publish content. Note that we do not store information related to individuals. Content added to the harmonized data model is indexed by Elasticsearch and mapped using ORML into RDF XML triples that are stored in a triple store known as the knowledge graph. The development of this knowledge graph is one of the main undertakings in ATHENA. Building a knowledge graph using semantic web principles yields several advantages. We are extremely precise and clear in our language when we describe the data that we capture. We can perform analysis such as reasoning or network analysis over the graph. Because we can link to other data sets and other data sets can link to ours, we enhance our ability to collaborate with other researchers, and publishing our content as a knowledge graph makes it easier for other researchers to reuse our data. Key to all of this is the reuse of existing vocabularies wherever possible. We make extensive use of well-established vocabularies in our graph. But it's not just about what we can do, it's about what you can do too. We expose several APIs, including REST and GraphQL, to facilitate interoperability with other tools such as OpenCTI and MISP, and to empower the more technically inclined amongst you to build tools that query and use our data. New data is also sent to the FIMI toolbox, where the various analyzers process the content to generate insights. The results generated by these tools are written back to the harmonized data model, where they are again indexed by Elasticsearch and stored in the knowledge graph. There are four types of tool in our toolbox: text analysis tools, image and video analysis tools, network analysis tools, and decision support tools. All of these are hooked into an event-driven system, which means that they process data as soon as it is added to the harmonized data model. Finally, we have the dashboard, which can be used to query the knowledge graph and harmonized data model. We won't see much of this module today as it's still in the design phase. Now let's see some of these tools in action. We will begin by looking at the FIMI toolbox, as an awareness of the tools available will be helpful when exploring our data later. As you can see, we have 4 different text analysis tools currently deployed from the University of Cyprus. 2 tools for assessing the apparent reliability of a news source or article. 1 tool for classifying text as hate speech, and 1 for performing named entity recognition. We have also integrated a deepfake analysis tool developed by Storzy, which can be used to assess whether or not an input image is likely to be a deepfake. We are currently in the process of developing network analysis and decision support tools, and have a number of other text and image analysis tools in development. Like the data sourcing engine, the FIMI toolbox is quite modular, and adding new tools is quite easy to do. Let's see some of these tools in action. We won't try all of them, but we'll show off some of the highlights. We'll begin with the binary news reliability classifier. This classifier is a simple binary classifier that will produce a label of either reliable or unreliable for an input text. The classifier uses various linguistic features of the text to arrive at a score. It is built using a multilingual language model, meaning that while this demonstration will be performed in English, the model can handle other languages. We will use as a sample input the headline from a Pravda news article. Although there is nothing malicious behind this headline, I think we can agree that it is unlikely that a giant doll is the source of escalating fear of war across Germany. We'll run this through the classifier now. We indeed see that it returns a score of unreliable for this headline. The binary reliability classifier is connected in series with a multi-class classifier. If an input text is found to be unreliable, then it is forwarded to the multi-class classifier to determine the nature of the unreliability. If we take the same headline, we can pass it into the multi-class reliability classifier. Here we see that this headline is likely to be satire or possibly clickbait. The deepfake analysis tool can be used to assess whether or not an image has been digitally manipulated, producing a probability score based on its confidence in the produced label. If we upload an image to the service, we can see the return probability that an image is or is not fake. In this case, we have a 99% certainty that this is a deepfaked image. Each of these tools are run automatically on the content harvested by the data acquisition module, with the results being written back to the harmonized data model. This allows the user to perform some highly sophisticated searches, such as searching for documents that mention the war in Ukraine and have a high probability of being unreliable. This, of course, brings us to the harmonized data model and knowledge graph. This dashboard is an internal testing tool that we use for exploring our database and testing out some ideas for tools and visualizations. On the left, we can see that there are links to browse articles, Telegram messages, and media objects that have been harvested from the web. We can also explore the different identities that can be linked to content that we have gathered. If we click into one of these, we can scroll through pages of data that ATHENA has identified and ingested from the internet. The true power of this system, however, lies in our ability to query and search over this data. Let's take as an example a simple keyword search for the word Zelensky. This returns a number of articles that have been harvested by ATHENA. If we refine our search to exclude articles with an unreliability score of less than 0.6, we can now refine our search results to a much smaller subset, which appears to be specifically targeted at Finland. Selecting an object gives us some metadata about where it was captured from. We can see the date on which the item was created, when we first observed it online, and when we last observed it online. We maintain a link back to the original item where possible, and can provide some previews of the content. We can also browse through the outputs of the analytical tools to see what scores were given to the content by different analyzers. Querying this data can also be accomplished programmatically, and documentation is available for those interested in querying ATHENA from their software projects. Thank you for watching this video to the end. If you would like to learn more about the ATHENA project, check out our website, projectathena.eu, for information, news and updates.